Hello, everyone. My name is Antoinette, and I am currently a member of Group 4. And today I will be presenting Chapter 16 on behalf of Group 4. And to start, we will be going over on how to understand the effect of conjugation on reaction mechanisms. So, what is conjugation? So, conjugation is a key idea in organic chemistry, and it happens when pi electrons spread out across neighboring atoms with altering single, double, and triple bonds. And this makes molecules more stable and reactive, directly influencing how fast chemical reactions can occur. So, for our topic overview, conjugation has a big impact on how molecules react by spreading out pi electrons, which make the molecules more stable and lowers their energy. This can change how fast reactions happen and which paths they take. So, conjugation affects reactions. These are included but are not limited to stabilization of intermediates, enhanced reactivity and addition reactions, selective electrophilic and nucleophilic attacks, energy profile modifications, UV and VI absorptions, and photochemical reactions, and applications in synthesis and design. By understanding these effects, we can predict and control how conjugated systems behave, highlighting why conjugating systems are so important in organic chemistry and its use. So next, we will be going over a couple of different misconceptions. And during those misconceptions, we will also go over debunking of those misconceptions and explaining how they may not always be 100% true. So for our first misconception, we have misconception one, and it is a single unchanging mechanism applies to all similar reactions. So this misconception is debunked because in reality, reaction mechanisms can vary based on conditions like temperature, solvent, reactant, and concentrations. And the same reactions may proceed differently under different circumstances. And this is something we will also be seeing in presentation number 2. So for our second misconception, misconception number 2, intermediates such as carbocations or radicals are always stable enough to observe. This misconception was also debunked because in reality, many intermediates are highly unstable and exist only briefly, often inferred through indirect evidence rather than direct observation. So next we will get into the quiz. These quiz questions are generally based on what we went over, just might have slightly different wording. So for question number 1, which of the following statements is true regarding the reaction mechanisms? A, reaction mechanisms are fixed and remain the same regardless of external condition like temperature or solvent. B, reaction mechanisms can vary based on factors like temperature, solvent, and reactant concentrations, even for the same reaction. C, reaction mechanisms are hypothetical pathways that are never influenced by experimental conditions. And D, reaction mechanisms are purely theoretical and cannot be tested or observed indirectly. So the first two I would cross out is both I would do A and probably D. But taking a look at this question, I would go for B because this is something we did speak about in our slides, especially when it came to temperature, solvent, and reactants. So question number 2, which of the following statements correctly describes reaction intermediates? So A, reaction intermediates are always stable and can be easily isolated in every reaction. So we can easily knock that one off because we do understand that these are not always stable. So B, reaction intermediates are highly stable and play no role in determining a reaction rate. So we can also cross that one out as well. So C, many intermediates are highly unstable and exist only briefly, often inferred through indirect evidence rather than direct observation. And D, reaction intermediates are never involved in chemical reactions and are purely hypothetical constructs. So I believe this question was actually pretty straightforward as it did come straight from our slides, which is C, many intermediates are highly unstable and only exist briefly, often inferred through indirect evidence rather than direct observation. So question 3, conjugation in a molecule decreases its overall stability by increasing the energy of the pi electron. So for this one, I'm actually going to go with C because it's not going to decrease stability. And for number 4, conjugated systems can influence reaction mechanisms by delocalizing charges across multiple atoms. This one I'm going to go with true, which is B, mainly because we do understand that even they can exist, especially briefly, showing that they can have an influence if they are true. So these are our answers. So next we'll be moving on to understanding the effect of temperature on the product distribution of electrophilic additions to conjugated dienes. So for this one, it's mainly going to discuss the temperature, the electrophilic addition to conjugated dienes. The product distribution depends on temperature. So for example, at low temperatures, the reaction is fast producing like kinetic product, but it's less stable, but it's going to form the quickest. And high temperatures, the reaction is slower, but the product of the thermodynamic product is going to be more stable. And this happens because temperature affects the energy and stability of the reaction pathway, allowing chemists to control which products they get. So an example that I use is it's like rushing to build a sandcastle, which would be the kinetic product, versus taking your time and making sure that it's sturdier, which is going to be the thermomatic product. Another way I like to put that is almost like when you're trying to cook a savory meal, you want to try to keep um, you want to try to keep as much grease in the pan. You don't want your grease to get everywhere. So that's what I can use for like when it's all the way up, you're going to get something quicker, but it might not be the best, which is going to be your kinetic or your thermomatic, which is something that you take time. It takes more time to cook, but that's when you get a better taste out of the food product. So for misconception 1, the product at low temperature is always the most stable. So this is a misconception. Students might think that because it can form at a lower temperature, but most temperature most stable because they assume stability is this the deciding factor for all reactions, but this was quickly debunked because, like stated earlier, low temperatures can form kinetic products, but it's gonna require it's gonna be a little bit faster, but it will be determined to be less stable, and the stability plays a bigger role in higher temperatures, which the thermomatic product is favored. So for misconception 2, temperatures only affect the speed of the reaction, and students may believe that temperatures only change how quickly the reaction happens, but it doesn't influence the type of product that is formed. So this was also debunked because in reality, temperature does not only affect reaction speeds, but it can also determine whether the reaction pathways leads to kinetic, low temperature, or thermodynamic, which is a high temperature, as stability becomes more significant at higher temperatures. So we will be going over our 4-question quiz. So question 1, which of the following is true about the product formed at low temperatures during the electrophilic addition and conjugated dienes? A, it forms faster, but is typically less stable than the product formed at high temperatures. B is always the most stable product regarding the conditions. C requires more activation energy than products formed at high temperatures. And D is the same product formed at high temperature. So for this, I'm going to go with A because it's referring to kinetic, which is going to have the lower temperatures. And it's also going to form a lot faster as well and be less stable. So for number 2, how does temperature influence the product's distribution in the electrophilic addition to conjugated dienes? A, it only changes how fast the reaction occurs without affecting product formed. B, at low temperatures, the aromatic product is favored due to its stability. C, temperature has no effect on the product distribution and the type of reaction. And D, at high temperatures, the aromatic product is favored because stability becomes more efficient. Excuse me, significant. And for this one, I actually am going to choose D, mainly because we do understand that aromatic products are going to have a higher temperature and they're going to have more stability as well. So for number three, higher temperatures in kinetic product favor electrophilic addition and conjugated ions. I'm going to say false because kinetic energy will typically have a lower temperature. And for number four, aromatic products and electrophilic additions to conjugated ions is more stable than a kinetic product. This is true. We understand that aromatic is going to have, it's going to be a lot more sturdier than kinetic, such as the sandcastle we talked about earlier. And so these are the answers. So finally, the conjunction happens when double bonds in the molecule are connected by a single bond, allowing electrons to spread out. This makes the molecule more stable and changes how it reacts, especially in electrophilic addition reactions. Temperature is also affects these reactions by influencing which products are formed. For example, low temperatures favor kinetic product, which form quickly but are less stable. High temperatures will favor aromatic product, which is more stable, but it will take a bit longer to form. Together, conjugations and temperatures help explain why some reactions produce different products under different conditions, allowing chemists to design the reaction for specific outcomes. These are my cited sources. Thank you so much, and I hope you enjoyed my presentation.
Hello, everyone. My name is Brianna Glanton, and this is my introduction to chemistry, my final presentation. Just going to be on two different topics. So I made a table of contents. 6.1, what are aromatic compounds? 6.2, the background and relevance of aromatic compounds. 6.3, which is actually my topic, one of them, do lone pairs participate in aromaticity? 6.4 would be the conclusion to that topic. And then 11.1 is my intro to amines. 11.2, my background and relevance of amines. 11.3, my second topic, which is determining the boiling point trends of amines, and then 11.4, which will be the conclusion to that topic. So to start off, since the first topic deals with aromatic compounds, we have to discuss what aromatic compounds are. Aromatic compounds are compounds that contain a planar ring of continuously overlapping p orbitals with 4n plus 2 pi electrons. And as you see right here, I have kind of a little list of some aromatic compounds. And you see that they are all planar, they are all in a ring, they have overlapping p orbitals, and they follow Huckel's rule, which is this 4n plus 2 pi electrons. Some notable ones would be benzoic acid, benzaldehyde. All right. So now we have the background and relevance of aromatic compounds. So first we're going to talk about the background of aromatic compounds and the origin of them being called aromatic. So many derivatives of benzene were originally isolated from the fragrant balsams obtained from trees and plants, and these compounds were therefore described as being aromatic in reference to their pleasant odors. So when you hear the term aromatic, you kind of think of aromatics or aroma, and that has to deal with smell and odor. Over time, chemists discovered that many derivatives of benzene are in fact odorless. Nevertheless, the term aromatic is still used to describe all derivatives of benzene, regardless of whether they are fragrant or odorless. So the name kind of just stuck regardless of most of these compounds not having any odor for real. So that's the background of aromatic compounds. And the relevance of aromatic compounds is that aromatic compounds are highly relevant in both chemistry and various industrial applications due to their unique structure and properties. Aromatic compounds serve as fundamental building blocks in organic chemistry. They are extremely, extremely stable, so their chemical stability allows them to participate in a wide variety of reactions. And aromatic compounds are prevalent in industrial, pharmaceutical, environmental, and agricultural industries, just to name a few. And as you see, I have some pictures right here. They are prevalent in pharmaceuticals, which is where you have your drugs and your over-the-counter medicine, stuff like that. In agriculture, mainly in like pesticides and things like that. And then you see I have some wine right here because they're in wine as well. And when you think of wine, you also think of aromatics as well. So, how do you determine whether a lone pair participates in aromaticity? There are a few rules for this. You have to ensure that the molecule is planar or very, very, very close to planar. You have to determine if the lone pair can delocalize into the conjugated pi system. You have to check the total number of pi electrons, including the lone pair's contribution, and see if it fits the 4n plus 2 rule, which is Huckel's rule for aromaticity. You have to consider the electronic structure of the heteroatom and its interaction with the pi system. And if the lone pair does contribute and the system follows Huckel's rule, which is once again the 4n plus 2 rule, then the molecule is aromatic. So we are talking about aromatics, so I do want to touch on these other two compounds. If a compound doesn't meet all of these rules, it is either anti-aromatic or it is non-aromatic. So anti-aromatic is kind of similar to aromatic compounds, being that it's cyclic, it's conjugated, it's planar, it also has no sp3 orbitals. However, the only difference is that it doesn't follow Huckel's rule, which is the 4n plus 2 rule. Instead of following Huckel's rule, anti-aromatic compounds follow the 4n rule. So no 4n, just no 4n plus 2, just 4n. However, if it doesn't follow that, or any of the other rules before that, then it is non-aromatic. And non-aromatic compounds are non-cyclic. They have sp3 orbitals. They are non-planar, and they have like an odd number of pi electrons. Another thing to touch on, like I said, aromatic compounds are very, very stable. However, anti-aromatic compounds are very unstable. And then non-aromatic compounds are pretty normal, somewhat in the middle. So now we can talk about the actual topic, which is, do these lone pairs participate in aromaticity? So as you see, I have three different compounds, and we will see they all have lone pairs. This one has more, but they all have lone pairs, and we'll determine if they participate in aromaticity. So as you see, we start with this one on the left. As you see, this lone pair right here is not a part of the pi system, so it does not participate in aromaticity. If you try to add it to the ring will be overcrowded and you just can't do that. So we can move on to the second one. This lone pair is part of the pi system. If you add it to the ring, you can make a bond right here. This bond can go right here, and this bond can go right here, and this ring will be fully conjugated. So this lone pair does participate in aromaticity. And then you see this one has two lone pairs. You cannot add both. You can add one, and then you can move the bonds, and it'll be fully conjugated. I'm sorry, but you cannot add both, or it will be overcrowded. So one of these lone pairs participates in aromaticity, but both do not. So one does and one doesn't. So now I have some misconceptions dealing with lone pairs and aromaticity. The first misconception is that all lone pairs contribute to aromaticity, which is not true at all. The actual truth is that only the lone pairs that are in conjugation with the pi electron system of the ring contribute to aromaticity. A lone pair that is localized and not part of the conjugated pi system does not contribute. So that's the first misconception. The second misconception is that a lone pair always makes the molecule aromatic. This is not true. The actual truth is that the molecule must meet the Huckel rule, which is 4n plus 2 for aromaticity. The lone pair must be able to delocalize into the pi system, and the molecule must have a planar structure to allow this delocalization. So I have a quick little quiz for this to see what we learned about lone pairs participating in aromaticity. We'll take this off and act like that wasn't there. The first question is, a molecule can be aromatic as long as it has 4n pi electrons, regardless of whether a lone pair is involved. This is actually false. Once again, in order for a molecule to be aromatic, it has to follow the Huckel's rule, which is 4n plus 2. Second question, which of the following is true about a lone pair that participates in aromaticity? The right answer is it should be in an orbital that can overlap with the pi system. Next question, what makes a compound aromatic? A compound is aromatic if it is cyclic, has no sp3 orbitals, if it is conjugated, planar, and follows Huckel's rule. Next question, a lone pair or an atom in an sp2 orbital can participate in a conjugated pi system if the atom is part of a planar ring structure. This part is true. And explain the difference between aromatic, non-aromatic, and anti-aromatic. Once again, aromatic and not aromatic and anti-aromatic are cyclic, have no sp3 orbitals, conjugate and planar. Aromatic follows 4n plus 2. Anti-aromatic follows 4n, and non-aromatic is non-cyclic, sp3 orbitals, and non-planar. All right, so that's it for this. So we can get back to this. And in conclusion, aromatic compounds are relevant due to their stability, reactivity, and wide range of application in fields. There are many steps to determine whether a lone pair participates in aromaticity. If a compound is not aromatic, it is either non-aromatic or anti-aromatic. So our next topic has to deal with amines. So what are amines? Amines are derivatives of ammonia in which one or more of the protons have been replaced with alkyl or aryl groups. As you can see, we have primary amine, which replaced one, secondary amine, which replaced two, and tertiary amine, which replaces three. So background and relevance of amines. Backgrounds, amines are a class of organic compounds that contain a nitrogen atom bonded to one or more carbon atoms. The general structure of an amine consists of a nitrogen atom attached to carbon atoms through single bonds. Amines are derivatives of ammonia, which you see right here, where one or more of the hydrogen atoms are replaced by organic groups such as alkyl or aryl groups. So why are amines relevant? Amines are relevant in both chemistry and various other fields. This is due to their chemical versatility, biological significance, and widespread use in industrial processes. They play huge roles in biological, pharmaceutical, agricultural, and environmental industries. Their presence in both nature and synthetic environments ensures that amines are central to life. And amines are in your vitamins, and they are also the building blocks of amino acids. So, what are the boiling point trends of amines? The boiling points of amines are influenced by the type of amine, the size of the alkyl group, and whether the molecule can form hydrogen bonding. Primary amines tend to have the highest boiling points, whereas secondary amines are intermediates, and tertiary amines tend to have the lowest boiling point. This is due to the absence of hydrogen bonding. As the alkyl group size increases, the boiling points of amines generally increases. These things all play significant roles in determining the boiling points of amines. So here I have three structures, and it says arrange these amines in order of highest to lowest boiling point. So as you see right here, this is a primary amine, so it automatically has the highest. This is a secondary amine, so it has the second highest, and this has more than 3 carbons attached to it, so it'll automatically be the lowest because of the lacking in hydrogen bonding. So the first misconception is that tertiary amines have higher boiling points than primary and secondary amines. The actual truth is that tertiary amines generally have lower boiling points than primary and secondary amines of similar molecular size. This is because tertiary amines cannot form hydrogen bonds due to the lack of hydrogen atom attached to the nitrogen atom. In contrast, primary and secondary amines can form hydrogen bonds, which leads to higher boiling points. The ability to hydrogen bond increases intermolecular attractions, raising the boiling point. So misconception number 2 is that larger amines always have significantly higher boiling points than smaller amines. The actual truth is that while larger amines generally have higher boiling points due to increased molecular size and London dispersion forces, branched amines may have lower boiling points than their straight chain counterparts of similar molecular weight. This is because branching reduces the surface area available for intermolecular interactions, which weakens the overall intermolecular force. So we have a quick little quiz on this one. I just want to take that off. Which of the following factors primarily influences the boiling points of amines? And the answer to that is the presence of hydrogen bonding. Second question, how do the boiling points of primary amines compare to secondary amines and tertiary amines? The boiling points of primary amines are higher than secondary and tertiary amines. This one says order the boiling point from highest to lowest. The boiling point from highest to lowest is primary, secondary, then tertiary amines. And this one says, what is the trend in boiling points for amines as their molecular weight increases? As their molecular weight increases, the boiling point increases as well. Which amine would have the highest boiling point? For this one, the answer would be methylamine, just because it has the most hydrogen bonding. So that's the end of the quiz. And then, uh-oh. In conclusion, amines are highly relevant in multiple fields due to their chemical versatility, biological significance, and widespread use in industrial processes. From serving as the backbone of amino acids and proteins in living organisms to being key intermediates in pharmaceuticals, polymers, agrochemicals, and more, amines play a central role in many aspects of modern life, and the boiling point of amines are influenced by the type of amine, the size of the alkyl group, and whether the molecule can form hydrogen bonds. And these are my sources. Thank you.
Hi, everybody. This is Kiera Goff, and today I will be discussing protecting groups and substituent effects. So good day, students. This is Dr. Goff back with another interactive lesson for my research symposium. First, I'd like to open up with protecting groups and the synthesis of compounds by converting alcohols into tert butyl and cellular ethers. Do you think that you can look over it? So what is a protecting group? First, we're going to debunk, then we're going to understand, and then we're going to apply. So, protecting group, a real life comparison. If you're painting a wall and you don't want paint to get on the window, you cover the window with tape or a plastic sheet. Once you're done painting, you remove the tape. So the official definition of a protecting group is a chemical group added to a molecule to temporarily hide a functional group, making it unreactive so other parts of the molecule can react selectively. For Grignard reagents and reactions, protecting groups are used to stop the alcohol from reacting with the Grignard reagent, which would race the reagent and form an unwanted byproduct. So the type of protecting groups we're going to be focusing on today are going to be tert butyl ethers and cellular ethers. So the first misconception is that protecting groups always react in an SN2-like mechanism. And we can debunk this mechanism because steric hindrance, electrophilicity, size, and bond length can affect the mechanism. And here are some work examples.
So in the first example, we are going to protect our alcohol. So the first thing that we want to do is isolate our isobutylene. Then we're going to protonate the double bond to create a Markovnikov carbocation. So by doing this, we are going to use an acid. By doing this, we have now installed a carbocation, a tertiary carbocation. By doing this, now we can attach it to our oxygen group on our alcohol. Because the alcohol is going to attack our carbocation and give our electrons to the oxygen. So by doing that, we now have a tert butyl ether on it. And it's going to be positive charge. Then we have our bromine still. After that, we want to get rid of our positive charge, so we're going to use the conjugate of the original acid. So we're going to use O, SO3H minus, and then we're going to take one of the lone pairs to attack the hydrogen and then break the bond between the hydrogen and the oxygen, because OSO3H is used to be protonate because the ether is unreacted to the alkanide, which is going to be our triple bonded carbon, which we're going to add on. So what we want to do is react the alkanide with the alkyl halide. So that's going to be our bromine over here. And it's going to go in an SN2-like mechanism. And the ether is going to be, after we do that, we also generate our ether. So let's try that out. Like I said, this is going to be our protecting group because the ether is unreactive to the alkanide. So once we do that, then we have this. we're going to take an alkali or a triple bonded carbon with a negative charge on the end. We're going to attack our alpha carbon and then get rid of the bromine because that is a great leaving group. So in this case now, you generated so now what we want to do is to deprotect so that we can have our alcohol group back. So what we're going to do is add a mild acid. So we're going to add H2SO4 and H2O in order to completely remove the ether. So we add doing that, we is hello class. Today we will be discussing protecting the mechanisms again. So in this reaction, will the reaction proceed by an SN2F mechanism or not? If you said yes, then you will be correct. So let's begin. First thing we want to do is take a compound like chlorotrimethylsilane to react with the alcohol group in the molecule. So by drawing it out, yeah. And so we're going to take one of the lone pairs from the oxygen, attack the silicone, and then boom. So this is kind of like SN2 because if it was SN2, it would be attacking the alpha carbon, and then breaking the bond between the carbon and the leading group. But in this case, we're using silicone. So now we have a positive charge on that oxygen because we lost the lone pair, and we're adding on that SiMe3, and the Me is going to be our methyl group, so CH3. So now we have that. What we should do is use a base like ET3N or imidazole to help remove the hydrogen from the alcohol. So this allows the silicone atom in the original reagent to attach to the oxygen atom of the alcohol. So like this. Like the bond between hydrogen and the oxygen. So we're now getting rid of the positive charge. Now, once you don't have the protection complete, we have created a serial ether group. So now our compound is like this. And that's also the same as OC. So we also write it as this. Now we're going to add our grain group. We're going to, in the counterpart we have sandwich, we're going to add pH and GPR. And then we're going to have our H3O plus because that is going to be our acid here. And so we're going to need a fluoride source in order to remove the cellular ether and restore alcohol. So we're going to use, we can use TBAF or TAF. So we're going to use one of the ions from TBAF, or 40 ions. And we're going to write this one. That's our fluoride source. And then we're going to attack that silicone. And then we can between silicone and oxygen. So now we've completed our grain yard. And we have gotten rid of that cellular ether. And so we're going to add H2O to protect that alcohol. And we have our final product.
So next we have a quiz. So the first question is, what condition would most likely remove a terbutyl ether protecting group? If you said strong acid, such as HCl or H3O plus, you would be correct. Why is trimethylsilyl chloride less sterically hindered than terbutyl chloride? If you said that the silicone carbon bonds are longer, you would be correct. What is the first step of protecting an alcohol? If you said protect the hydroxyl group by replacing its proton with a protecting group, You would be correct. Which of the statements about SN2 life mechanisms are true? You said these two options. You would be correct. And then, is this possible? Is this product possible? Think about it. As the reaction can occur. Good job. Next. Good job, guys. You did amazing. Now we need to go over the effect of substituents on the rate of electrophilic aromatic substitution. Are you ready? So, directing effects of a substituent. We're going to debunk, understand, and apply. So there are three different types of directing groups. We have meta group, which is going to be a 1,1,3 director, and it's deactivator favored, and it corresponds with electron withdrawing groups. Ortho is going to be 1,2 or 1,6, and it's going to be activator favored and steric crowding. And then para is going to be 1,4. It's activator favored, less sterically hindered, and it is electron rich. So the first misconception is that an ortho-para directing substituent can be added in the ortho position with no substituent occupying the para position. So we're going to debunk that because a blocking group is required to push a substituent ortho directing instead of para directing if there's no substituent occurring at the para position.
Hello class, today we will be discussing blocking groups. In example 1, we have a benzene ring with a hydroxy group, and we want to add our chlorine to the ortho position. Normally, we would have our chlorine in the para position, but since we want it in the ortho position, what do we have to install? If you said a blocking group, then you would be correct. So, what we're going to do is add a good blocking group. And by adding fuming H2SO4, we're going to do sulfonation, and we're going to add SO3H to the ortho or para position. If you said para, then you would be correct. Is SO3H a meta or ortho-para director? If you said meta director, then you would be right. So now we want to add a chlorine. Since it's a meta director, we're going to add a chlorine to the third position in respect to the SO3H. So we add a chlorine here. So now we're almost done. We want to get rid of our SO3H. So what are we going to do? We're going to dilute the H2SO4 in order to remove our blocking group. By doing that, we now have our final product. In the ortho position. Good job. Okay. So in the reactant, which substituent is going to be an activator? If you said this group, then you would be correct. So, would we want the bromine to go in the ortho or para position? If you said para, that'd be correct. Because of what? Less steric hindrance. But in the product, we have it in the ortho position. So what would we have to do again? Add a blocking group. So let's go through the same process. Let's see. What could I add to the para position? Fuming H2SO4. And by doing that, we're keeping everything the same and adding SO3H. What do we need to add to make the bromine go to another position? Br2, Fe, Br3. And where would the meta position be? Let's draw it out. Not to get rid of the blocking group, what will we add? Dilute H2SO4. And give us our product.
So the second misconception is that Friedel-Crafts reactions cannot be performed in the presence of a weak deactivator substituent on a reactant. And so this is debunked because Friedel-Crafts can work with weak deactivators. Only mild and strong deactivators produce no reaction.
Starting with this benzene ring, we want to get our final product. So the first thing that we want to do is add our bromine. And we want to do this because we need our nitro group in the meta position to our ketone group that's coming off the benzene. So the first thing that we need to do is add our bromine because that pushes the next substituent to the para position. So next, what we want to do is nitration or Friedel-Crafts. We want to do Friedel-Crafts by adding this. Yeah. Is this an orthopara or meta director? This is a meta director. So therefore, now we can do nitration. We get our final product. Because even though the bromine is a weak deactivator, it is not too weak that we can't do Friedel-Crafts. Good job. Doing another synthesis problem. So first, we have a benzene ring with a chlorine attached to it. We want to perform Friedel-Crafts twice in order to get our product. So first, what we want to do is add our methyl group. And by doing this, we will add CH3Cl AlCl3 to add our methyl group para to the chlorine group. Now we have done that, we want to add our propyl group. But how do we get to propyl? So what we want to do first is we want to add our ketone. And we can do this by doing this. There's multiple ways to get this, but we want to add our ketone. So we'll add it. This will add AlCl3. So we can do this. And then we want to reduce this down to an alkane. So by adding a certain reagent, we can reduce this to a propyl. We're going to add ZnHg, HCl, and heat in order to turn our ketone into an alkane, a propyl alkane. And we have our final product. Good job.
All right, next we have another quiz. So, which of the following statements is going to be true? If you said the activator in orthopara, then you would be correct. How do electron donating substituents generally affect the rate of electrophilic aromatic substitutions? If you said they increase the rate by activating the ring, you would be correct. Can this reaction undergo Friedel-Crafts? If you say yes, it can. The iodine is a weak deactivator, you would be correct. If you add a substituent to the compound, can it go in the ortho position? Yes, it can with the addition of a blocking group. And can this reactant undergo a Friedel-Crafts reaction? If you said no, then you will be correct. Good job. So thank you for your help. I'm ready for my symposium. And these are my references. Thank you. Perfect. Oh, that took me forever. You see?
Hello, everybody. My name is Makaya Coley, and I will be presenting aromatic and anti-aromatic compounds, as well as nucleophilic aromatic substitution within addition and elimination reactions. And as well, this is just a review for Organic Chemistry 2 on some of the topics that we've been covering over this semester. So to preface, hello future scientists. It's time to learn some new concepts and new compounds. Today's lesson will teach you about aromatic and anti-aromatic compounds, their characteristics, their reactions, and some common mistakes that many students have. Let's start. So to overview, we'll be going over aromatic compounds, anti-aromatic compounds, Huckel's rule, common misconceptions that students have, as well as a quiz at the end that you can complete. So to start, we'll be talking about aromatic compounds. Usually with aromatic compounds, they have a planar structure, they're double bonded, conjugated within a ring, and they're cyclic. As well, conjugated means that there are alternating double and single bonds within a ring. As you can see in the aromatic compound picture at the top corner with the benzene, pyridine, and naphthalene compounds that are, again, conjugated with those alternating double and single bonds. And then when we recognize if they're an aromatic compound or not, we have to use a formula 4n plus 2, which counts the number of delocalized pi electrons that are found within a compound. So n represents the amount of pi electrons. For example, in benzene, the amount of pi electrons were 1. So you'll plug in 1 to n, you would get 4, and then you do 4 plus 2, which would equal 6 delocalized electrons that you would find within that compound. And even so, the numbers increase by 4. So you can have 2 pi electrons, 6 pi electrons, 10 pi electrons, 14, so on and so forth, when trying to recognize an aromatic compound. As well, the stability of aromatic compounds is fairly stable. And as far as reactivity, it is less reactive than non-aromatic compounds because of the way their electrons are positioned and the way that they interact with each other. And there's something else that we use as well within chemistry to differentiate between aromatic and anti-aromatic compounds, and it is known as Huckel's rule. In this case, for aromatic compounds, the compound has to be cyclic, planar in structure with a conjugated system, and there has to be an odd number of e electron pairs or 4n plus 2 total pi electrons, where n is either 0, 1, 2, 3, or 4. And by odd number, mean 2, 6, 10, 14, etc., so on and so forth. Now moving on to anti-aromatic compounds. Anti-aromatic compounds are cyclic, conjugated, flat, and overlapping within their p orbitals. As well, you have less stability within these aromatic compounds, and they are highly reactive because of the amount of delocalized electrons that it has and how they react to one another. So in this case, there is an equation. It is 4n delocalized electrons. So n represents every 1 electron. And usually you will have these compounds have their electrons come in multiples of 4. So when we look at Huckel's rule, you need 4 pi electrons, and anti-aromatic compounds come in multiples of 4. And then using the MO theory, which is talking about the orbitals within a compound, we can explain the rule. The compound lacks a closed shell, and the electron configuration is primarily unstable and is anti-aromatic. And you can see that within this structure, this is an anti-aromatic compound, and then this is the energy level, and then you can see the bonding orbitals of the compound, and that can tell us its stability or not, and it as well if it's anti-aromatic or aromatic. Next, we have a quick tip rule known as Huckel's rule, which again, that is the rule that we use to determine aromatic and anti-aromatic compounds based on certain structures and as well as the delocalized electrons. So for Huckel's rule, we can sometimes call it the 4n plus 2 rule as well for at least aromatic compounds. And as well, you can use the Frost circle. And the Frost circle is a diagram that helps visualize the molecular orbitals of cyclic compounds, and it can show the energy levels of pi electrons. So you can see the steps. First, you draw a circle, then you inscribe a polygon or just connecting points of the circle so that you have edges. And then you do horizontal lines at each point of the intersection. And then eventually you're going to erase the circle that the polygon was inside, and as well as the circle itself. And you can see the energy levels of the bonding molecular orbitals versus the anti-bonding molecular orbitals, and as well just the number of pi electrons that you have within a compound. So again, for this 4-member ring, you have 1. For a 5-member ring, you have 3. For a 6-member ring, you have 3 as well, 7, and so on and so forth. But again, this is for molecular orbitals. And so when you read it, for an aromatic compound, the electrons filling the molecular orbital should be such that the lowest energy molecular orbitals are fully occupied, meaning pi, and that the total number of pi electrons is equal to 4n plus 6. And then for anti-aromatic compounds, the total number of pi electrons is equal to 4n. Excuse me. And there are degenerate orbitals that are half-filled compared to the aromatic compound that has fully filled orbitals. So first, we'll dive into our first misconception of aromatic and anti-aromatic compounds, which is that all conjugated rings have aromatic stability. Now, what defines aromatic stability? It is when a compound is cyclic with a ring-like structure, conjugated, the electrons are delocalized, and it obeys Huckel's rule in all cases. In this case, this has been debunked. So when we look at these two compounds, cyclobutadiene and cyclooctatraenine, you can see that they are all both conjugated, and as well they have pi electrons that exist within their compounds. But just because a compound is conjugated, it does not mean that all of the electrons are properly dispersed. So if they're delocalized or not, or even so how they interact with each other. And so these ones are prime examples of how conjugated compounds that do not have stability. So just because they're conjugated with those electrons that are delocalized, it does not mean that it is stable. So for cyclobutadiene, it doesn't satisfy the 4n plus 2 rule for electrons when it comes to aromatic compounds. It has 4 pi electrons. Therefore, Huckel's rule is not met and is not aromatic or stable, but that means that it classifies as an anti-aromatic structure. For cyclooctatraene, it does not satisfy the 4n plus 2 rule for electrons. It has 8 pi electrons. And this structure is non-planar, meaning electrons cannot delocalize, and it is an unstable structure. Most of the time when we see compounds that are conjugated that have a electron that does not obey the 4n plus 2 rule, it is usually unstable because of the way the delocalized electrons are interacting. And so this is just a quick little joke. If you can read it, it's a unstable anti-aromatic compound versus an aromatic compound, and the anti-aromatic compound is unstable versus the aromatic compound, which is stable. Next, we have our common misconception 2, which is that anti-aromaticity means a lack of delocalization, specifically within electrons. So first, let's define anti-aromaticity and delocalization. So anti-aromaticity is a compound that is anti-aromatic. It is cyclic, conjugated, has 4 pi electrons, and is unstable with delocalized electrons. Now, what are delocalized electrons and how does it relate to delocalization? So delocalization occurs when electrons are not confined to a specific bond. And this is when compounds are conjugated, the electrons can be shared between the atoms. And this will cause a delocalized electron cloud where all of the delocalized electrons are existing around the structure. And in the picture, you can see the p orbitals and then where the delocalized electrons will exist around the compound and around the structures that you have. So you have the electrons existing outside of here and outside of here, and then you have them right here. And so, again, this has been debunked that anti-aromaticity does not mean a lack of delocalization. It doesn't. Anti-aromaticity compounds do have delocalized pi electrons, meaning that they do have delocalization. Some examples include the ones that we saw before in the previous slide, as well as pentylene, and they all exist in rings, have delocalized electrons, and meet Huckel's rule of 4 pi electrons. And then you have pentylene here, which again exists in rings. It has delocalized electrons around here. And then we have a picture that shows delocalized electrons in the outer shell electrons and how they orbit around different compounds. And so that's just an example of what we will call a delocalized electron cloud as well. Next, we have nucleophilic aromatic substitution and addition-elimination reaction. So, nucleophilic aromatic substitution is a specific type of nucleophilic substitution that occurs on aromatic compounds, typically those with a conjugated planar ring system, such as benzene, and a leaving group attached to one of the carbons in the ring. And this is a different mechanism to the more common electrophilic aromatic substitution, which involves an electron withdrawing group in the aromatic ring, which is stabilized with an intermediate during the reaction. With this one, we have a nucleophile that is attacking a certain compound, and then we have a loss of a leaving group afterwards. And as well, we have a compound that is formed in the middle as a complex known as a Mesenheimer complex. And again, this one is just an example of how this group would be leaving at the end of our reaction, and it would be replaced by something else towards the end. And so in the first example, you see chlorine that is being attacked by a nucleophile, and then we have the delocalized electrons moving to form a bond and delocalized electrons moving to form another bond. And as they're moving in these reactions, it's known as a Mesenheimer complex. And then at the end of the reaction, we will have the leaving of the Cl here and being replaced by an OH up here. Next, another common misconception is that nucleophilic aromatic substitution and SN1, SN2 reactions are the same. This has been debunked. Nucleophilic aromatic substitution occurs by an addition-elimination mechanism. And in this mechanism, the nucleophile attacks the electrophilic carbon here, and then it forms a resonance-stabilized intermediate, which is here, the Mesenheimer complex, and then afterward, the leaving group departs, completing the substitution. So this leaving group of F will depart and be replaced by the OH at the top of the compound. But in comparison, an SN1 mechanism involves carbocation formation and a nucleophilic attack. And in this one, you just have a different type of intermediate that is formed. So the middle step is going to be different in an SN1 reaction. In an SN2 reaction, this is a one-step process where the nucleophile is attacking the electrophilic carbon at the same time with the departure of a leaving group. There is no intermediate found, and the reaction proceeds with a single transition state. And as well, this is where the nucleophile attacks and the leaving group departs. Next, another common misconception is that the addition step of addition elimination is simply a nucleophilic attack. This has been debunked. The nucleophilic attack happens on the carbon attached to the leaving group, forming a Mesenheimer complex. This is then stabilized by the electron withdrawing groups in ortho or para positions. So in this example, we can see the nucleophile, hypothetically, going in and attacking this carbon that is attached to this leaving group, the LG, and then you have the delocalized electrons attacking this as well. And then once that happens, you have the moving of these double bonds within the conjugated ring, and then you have a electron-rich intermediate, which is the Mesenheimer intermediate because these electrons are being donated. And then you have the loss of a leaving group, and then the nucleophile replacing the compound here. So lastly, we have a review of So You Think You're Smarter Than a Scientist, and students can go onto the Google Doc and be able to recognize aromatic compounds, anti-aromatic compounds, and as well as using the equation within Huckel's rule to determine if they're anti-aromatic or aromatic. And so in conclusion and in summary, aromatic and anti-aromatic compounds represent two different classes of molecules based on structure, their reactivity, and stability. Our means of classification come from Huckel's rule as well as other characteristics. These are our references. And then thank you so much for playing Guess the Compound. You guys have a great evening.
Hello, so today we're going to be talking about aldehyde and ketone reactions as well as peptide sequencing. My name is Sonaria Johnson. So first, before we even get into it, I want to give a little bit of background info. So the first topic we're going to be talking about is the aldehyde and ketone reactions. When I say carbonyl carbons, I'm talking about the C double bond O. I'm talking about that group. And aldehydes are going to be carbonyl groups with a carbon and a hydrogen attached. So that's how you can identify that a material is an aldehyde. A ketone is going to have 2 carbons attached to your carbonyl carbon. And again, your carbonyl carbon is going to be your carbon that is attached to your oxygen. A peptide bond is going to be a covalent bond that forms when you have 2 amino acids that are attached together. So that's going to be your carbonyl carbon from your carboxyl group and your nitrogen from your amino group. And then we're going to get more into all that entails later on in the presentation. And so the initial concepts we're going to be talking about is comparing acid catalyzed and base catalyzed addition of water, which is going to be hydration, in comparison to aldehydes and ketones. And then the second part of the presentation, we are going to use 1-letter abbreviations to show the sequence of amino acid residues when provided the structure of a peptide. So the next slide, we're just going to do a little bit of pre-test knowledge. It's just a little pre-test. So I have a question. Which is true about aldehyde and ketone hydration? A. Water reacts directly with the carbonyl group in aldehydes and ketones. Or B. Acid catalyst is necessary to facilitate the hydration reaction. So the correct answer is going to be B. Although A is correct, water does react with the carbonyl group, acid catalyst is necessary in order to facilitate the hydration reaction, because your catalyst, whether it's acid or a base, is going to activate the carbonyl carbon so that your nucleophile, which is going to be water, or an hydroxide ion, if you're doing base catalyst reaction, you're going to need a catalyst to activate the carbonyl carbon so that it can be able to be attacked by a nucleophile. So first we're going to be talking about acid catalyzed hydration. Before we even continue, you should be able to identify which picture on the left or the right has aldehyde as a starting material or ketone. So we're going to go, so the left is going to be your aldehyde because you have the carbon and the hydrogen attached to your carbonyl carbon. While on the right, you have the ketone because you have 2 carbons or 2 methyl groups attached to your carbonyl carbon. So I'm only going to go over the mechanism on the left side because the reaction mechanism for both aldehydes and ketones in acid catalyzed hydration is basically the same. You just have different products. So in step 1, you're going to start with the protonation of your carbonyl. This is going to make it more electrophilic so that your carbonyl carbon is more readily available to be attacked by a nucleophile. In this reaction, your proton or your H, your hydrogen, is going to be your acid. So your oxygen will be protonated with the hydrogen. This will create a protonated carbonyl intermediate. And both of these resonance structures can be attacked by the water. Your second step is going to be a nucleophilic addition. Your nucleophile will be your water. So your water is going to attack your carbonyl carbon, and the electrons in the double bond will move to the oxygen to create a neutral alcohol. Then your last step will be deprotonation. So you're going to get another water, and it's going to remove one of the hydrogens from your group, and then the electrons in that bond will move to your oxygen, which will result in 2 alcohol groups. So that's going to be your geminal diol. Whenever you see a acid catalyzed hydration or a base catalyzed hydration, your product is going to be a geminal diol. And so for ketones, that's going to be the same thing. Your mechanism is going to be fairly the same. In the acid catalyzed hydration of aldehydes, you're going to have a faster protonation because there is going to be less steric hindrance. And that's going to come up a lot in this presentation. Aldehydes are just less sterically hindered because ketones have 2 methyl groups, which make it more sterically hindered, while aldehydes only have the carbon and the hydrogen. Acid catalyzed hydration in ketones, your protonation and your water attack is going to happen more slowly because, as said before, your ketones have more steric hindrance and has bulkier groups around the carbonyl carbon. And then on to the next slide, we're talking about base catalyzed hydration. So again, the picture on the top is going to be your aldehyde. The picture on the bottom is going to start with your ketone. Base catalyzed hydration is going to be similar to acid catalyzed hydration. The only difference is you only have 2 steps. And so the first step is going to be your nucleophilic attack of your hydroxide ion. So the hydroxide ion is going to be the OH minus. So that's going to attack your carbonyl carbon, and then the electrons in the double bond will move to your oxygen, creating an alkoxide ion. Your next step will be protonation of your alkoxide ion. So it's going to be protonated with a hydrogen from water, which will result in your 2 alcohols or your geminal diol, and that's going to be the same thing for ketones as well. The only difference is, as stated before, in ketones you will have a slower reaction because of bulkier groups, and in aldehydes your hydroxide ion will attack the carbonyl carbon more easily because of less sterical hindrance. A misconception is that acid catalysts are unnecessary for hydration reactions. And this is untrue. Acid catalysts are essential for protonating the carbonyl oxygen. And as we also said before, it makes it more electrophilic, which makes it more prone for a nucleophilic attack, which allows you to add your water more effectively. A second misconception is that all carbonyl compounds react at the same rate in hydration reactions. And as we also said before, aldehydes are they're less sterically hindered, and ketones are more sterically hindered. So aldehydes are going to be more reactive because they're more readily to be prone to a nucleophilic attack. And that's in both acid and base catalyzed hydration. Aldehydes also have higher electrophilicity, so that's also the reason why they would not react in the same rate. On the next slide is going to be a quick little quiz. It's about 5 questions long. It's just testing your knowledge about acid and base catalyzed hydration. Now we're going to be talking about peptide sequencing. So peptides, as we stated in the first slide, is going to be a short chain of amino acids linked together by peptide bonds. And they can range from a few amino acids to longer chains that form proteins. And your amino acid sequences are going to be the specific order in which amino acids are arranged in a peptide or a protein. And this determines the structure and function of the molecule. And so we're going to go back to the first slide. in this little bubble, I have a peptide bond forms when the carboxyl group of one amino acid reacts with the amino group of another, forming water. So, if you look at the picture of the peptide bond or the peptide chain, you have your carbonyl carbon attached to the oxygen, and then you have your amino group. Now we know amino groups normally have one nitrogen and three hydrogens. And peptide bonds actually, in your carboxyl groups contain a carboxylic acid functional group. So while the picture does not show it, there actually was a oxygen attached to your carbonyl carbon. And so if we have two hydrogens from the amino group and an oxygen from your carboxyl group, you have water, H2O. So that's why it forms water when you create a peptide bond. What amino acids represent the peptide sequence? A peptide sequence like AGS represents the amino acids alanine, glycine, and serine in that order. It's very important that each amino acid matches up to each letter. The 3-letter sequence would be ala, gly, and ser. You can tell that this first amino acid is alanine because of the methyl group attached to the alpha carbon. The alpha carbon is going to be the carbon between your amino group and your carboxyl group. And that's how you can tell that's alanine. Glycine is just going to be your amino group and your carboxyl group. Serine is going to be your amino group, your carboxyl group, and then a hydroxyl group attached to a carbon attached to your alpha carbon. That's how you can identify serine. And that's going to be the same for all 20 of these amino acids. There's different polarities and different side chains that can be used to identify the amino acid. And this is going to be your full chain. A misconception is that peptides are sequenced from the C-terminus to the N-terminus. And also, one way to remember it is that your C-terminus is going to be your carboxyl side. It's going to have your carbon, your C. Your N-terminus is going to have your amino side with the nitrogen, your N. And so that is the misconception, because peptide sequences are always going to be written starting from the N-terminus to the C-terminus. That is how you can also identify what your amino acid is, looking at the N-terminus and then finding your C-terminus to determine which amino acid you have in your chain. Another misconception is that the order of amino acids doesn't matter for peptide function, and this is untrue. The sequence determines the peptide structure and function, making it very important. I also have another 5-question quiz here, and then these are my sources. Thank you so much.
Welcome to Dr. Jess's lab. We're going to go to the basics. I am doing misconceptions and concepts of both intermolecular forces and Huckel's rule. So we are doing this as a slideshow where you are able to select where you want to go first, but we're going to go in order. So we're going to start off with intermolecular forces. So selection 1. When we're talking about intermolecular forces, we are talking about the forces that occur between molecules. So inter meaning between, and molecular meaning molecules. We will discuss the difference between inter and intramolecular interactions. But basically, intermolecular forces are forces that affect the bonding of molecules towards one another and the attraction or repulsion of these molecules with each other, and how they affect the boiling point. So as we know, the boiling point, as I said, is causing a liquid to boil or go from a liquid to a gas state. So it takes energy and release of energy for that to happen. And that is just basically just breaking down bonds. And to do that, you have to typically raise the temperature. If you were to lower temperature, things would freeze and break down those bonds and cause them to compact. When you boil them or heat them, they become to break off and break off frantically, like gas, as we know, is very free moving. So intermolecular forces affect your boiling point because the stronger the interactions between your molecules, the less they want to break apart, right? So your boiling point is going to rise, and we will get into deeper. That this is just a 30,000 foot view of intermolecular forces and their input or effect on boiling points. So our first misconception is that electronegativity is the only type of intermolecular force. That comes from basic chemistry in the very beginning when you do learn about, your neutrons, your protons, your electrons. You get to thinking, okay, well, the bigger the electronegativity, the stronger their bonds to other smaller molecules. And while that is true, there are several forms of intermolecular forces. So as we know, if you have a periodic table, as you go diagonal or up and across, then you have a higher electronegativity. So as we know, hydrogens and those smaller molecules are on one side and they're on your small side, where you start going across and you have carbons, you have fluorines, you have bigger molecules, and they have higher electronegativity. And while that does play a role and goes into our dipoles and ionic, we will talk about that in our next slide, but it plays a role in the connection. So our first misconception is that electronegativity is the only type of intermolecular force. That is not true. And the fact is that you have multiple forms, and electronegativity itself is not an intermolecular force. Electronegativity is a property of individual atoms that determine polarity of a bond, which can influence the strength and type of regular forces that exist between molecules in that bond. Therefore, electromolecular forces can be influenced by electronegativity, but electronegativity actually has nothing to do with intermolecular forces at all. They're proportional, or as like scientists like to say, they are correlated. So intermolecular forces themselves, we would say with things are London dispersion forces, dipole forces, hydrogen bonding, and ion dipoles. Ions, which dipoles are typically what you are talking about when you think of electronegativity. Then you have dispersion, which is how the atoms and their charges are dispersed in a molecule that make them attracted to each other. You have dipole, as in polar versus nonpolar, and the most common one is hydrogen bonding, which we will get into later. Our second misconception we have is that all intermolecular forces have the same impact or strength on boiling points. We know this is common to think. You would think that, okay, if you've got some electromolecular forces going on, then your boiling point's stronger. And while that's true, they have different effects because they affect how molecules are bonding and interacting with each other at all times. So that is a misconception. And the facts are each intermolecular force has a different impact on molecules, and typically hydrogen bonds are the strongest form of intermolecular forces, as hydrogen has one electron to share and essentially is selfish. So that is why you hear hydrogen bonding being your strongest intermolecular force. It should be your strongest intermolecular force, considering that hydrogen is your smallest atom with just one, and whatever it bonds to, it wants to stay with. It's not like carbon that's got, four arms, I should say, ready to grab and hold on monkey style. Hydrogen is selfish and does not want to leave. And that is why it bonds so well with oxygen and makes water. So oxygen, we know, is made up of 8 for an octet, but 2 to be calm, because oxygen is reactive. So to be calm, you have your hydrogen, 2 of those bond with one oxygen, and oxygen is totally cool. It's going to have some lone pairs or whatever, but the lone pairs will be stabilized and not too reactive. So that's why water is such a strong molecule and has such a high boiling point for something that is so small. It only has technically 2 atoms involved, right? Oxygen and hydrogen, but it has a very high boiling point compared to a lot of other molecules, simply because hydrogen doesn't want to bond and oxygen doesn't want, or hydrogen wants to bond and oxygen likes being bonded to. Now, our last misconception is that intermolecular forces are the same as intermolecular forces. To me, this is our biggest misconception and is the most important to dive into. I spoke about it a little bit earlier. So inter and intra. Inter meaning in between, intra being inside. So the facts for this one, sorry, I'm in the way. They are similar, but they are different. So intramolecular forces are forces that hold atoms together within one molecule itself, while intermolecular forces that we are talking about today are the forces of attraction and repulsion that exist between different molecules. So that is going from, when we talk about water, intramolecular forces of water and the hydrogen and oxygens together versus intermolecular forces, which would be water to water. Okay, awesome. Now we're going to have some real life examples. It's not very hard to do. We can go back to water. As we see, water is very hard to split. It's very hard to boil. It's kind of hard to actually freeze as well. So we see that because oxygen is always ready to bond, and it has 8 valence electrons always free to bond. So when you have hydrogens just floating in the air, floating in the atmosphere, they are very abundant naturally. Then you have those molecules that are not willing to really separate. And that is different from what we see as the covalent bond, which I was referring to in water itself, the intramolecular force of oxygen with its 2 hydrogens not trying to leave and sharing molecules. It also says that most covalent bonds form between nonmetals. And that is because, again, goes back to electronegativity and desire to bond, and also amount of valence electrons able to bond. So just to wrap things up, as we see, hydrogen bonding occurs between hydrogen and other atoms present in molecules. So that is what we know as the strongest intermolecular force. And then regular bonds, such as ionic bonds or covalent bonds, we see occur between atoms sharing electrons. So this makes intermolecular interactions dependent on molecules, while intramolecular interactions are dependent on atoms. That is the best way to remember. If we are talking about atom to atom, periodic table letter to periodic table letter, we are talking about typically intramolecular forces. And we are talking about molecules as in water to, or how we do it in chemistry all the time when you're having these reactions. So maybe you are adding water to something, taking water out of something. Maybe you have a boron getting reacted to a sodium, something. That is what we're talking about intermolecular forces, where those are going to now have different effects and different strengths on boiling points and their interactions, and even bond, what else, stereochemistry, stuff like that. So another real life problems worked out, because again, this goes back to the strength and how we understand the interaction of boiling point. Boiling points of molecules are heavily impacted by the amount of and specific type of intermolecular forces present between each bonded atom. So the molecular weights for these go up, but are roughly all the same. And when we see that they have London dispersion, we have dipole-dipole, and we have hydrogen bonding. When you see that 3 out of the 4 of these don't have hydrogen bonding, but the one that does has a significantly higher level of intermolecular force interactions and higher boiling point, we can see how each one has a different strength. So for cyclopentane, only has London dispersion forces, which is fine, no shade, but he has a very low boiling point and the least amount of intermolecular force reactions. Then when you jump to THF and butanol, these things have London dispersion and dipole-dipole, but they don't have hydrogen. They don't have hydrogen in there. So these oxygens are still relaxed. They have their 2 bonds with carbon, which is a stronger, who is willing to also bond because it has 4, right? So carbon's kind of chilling, oxygen's chilling. No hydrogens present except for on the carbons, which we're not talking about. So everything's pretty cool, as our boiling points are minimal. Mind you, this is Celsius. Keep that in mind. Because if 118 Celsius is if 0 degrees Celsius is what 128, it was on a previous slide, then 118 degrees Celsius Fahrenheit is probably 3 something. So very, very high boiling point. So 66 and 75 would be very moderate boiling point. Still hot for Fahrenheit, but not that much. When we see butanol, which we know has alcohols, and now it has that hydrogen there. And not only is oxygen attached to the carbon, but it's attached to a hydrogen. And now things are getting, hey, I don't want to leave, and you don't want to leave, and we're not leaving. All right. Best way to put it. Simple, but successful. All right. So are you ready to test our knowledge? I hope we are, because we don't have any choice. So we're going to go ahead and go to our Kahoot. And let's see. Is it still sharing? I don't know what you can see. Oh, okay, you can see everything I can see. Cool. Let's see. True or false? Intermolecular forces are forces that hold atoms together. That keyword atom, right? That is why I made that note. It's got to be false. Cool. And how do intermolecular forces impact a molecule's boiling point? I don't know. They have no impact on boiling points. They only change the boiling points if hydrogens are involved. That's a good trick question. You might want to use it. Determines where bonds go, move once molecules apart. Determines the strength of bonds and how long molecules will break apart. I think that's the right one. Awesome. You can use Huckel's rules for molecules that contain more than one ring. Let's watch a short YouTube video to make sure we really got it. Let's see what we've got here. What is an intermolecular force? A push or pull exerted on the object to change its motion or shape. I believe that's just force. F equals m times A, also just force. Okay, now we have hold atoms together within a molecule or interactions between molecules. So that's going between inter and intra. It's time for our quiz. I mean, I did make this, but hey, I could still mess up. We're trying to win here. Which one of the options below is not an example of intermolecular forces? Hydrogen bonds, dipole, dipole, covalent, or covalent, we talked about that. Something tells me. You can use Huckel's rule on non-cyclic or polycyclic modes. Yeah, man, we're too smart for that. Versus cited.